Okay, section 3.3 dealt with the first derivative and some of its applications, and in section 3.4 we want to look at the second derivative and some of its applications. And so the first thing I want to remind you about is the concept of concavity. And so concavity describes the curvature of a graph. We talked about this a little bit last year. If a curve is concave up, I want you to think of a bowl that's sitting upright on a counter. Okay, so that red curve there on this graph is concave up because it's opening upward. So always think of the opening. Don't think of where the vertex is, but think of the opening of the graph. And so it's opening upward, so it's concave up. And then so that means that that green one is concave down. Now, you'll recognize probably that these two graphs are parabolas. And so the red one, since it's opening upward, since it's concave up, we would know that what we call a for that parabola, ax squared, the leading coefficient, is going to be positive. And we know that for the green one, that a value would have to be negative. So if we look at a little closer at these two curves, you'll see that I've given you the equation of the red one. It's f of x is 1/4 x squared. And if we take the derivative of that, we get 1/2 x. And if we take the derivative of that, we get 1/2. So what we see is that these functions that are concave up, they have a second derivative that is positive. And in the same way, if we take that green curve, it has the equation negative 1/3 of times x minus 4 squared plus 2. When we take the first derivative, we get negative 2/3 times x minus 4. And when we take that second derivative, we just are left with negative 2/3. And so because that leading coefficient was negative, then this second derivative turns out negative. And what we're going to see is that any function that has a second derivative that is negative, that part of its graph where its second derivative is negative is always going to be concave down. Now, if we have a part of the graph where the second derivative is 0, for example, think about a line like y equals 2x. Of course, if we take the first derivative, we get 2, and second derivative, of course, then is 0. And that makes sense, because if you think about it, a line doesn't have that curvature. It's neither concave up nor concave down. So if the second derivative is 0, then we have that occurrence where the graph is neither concave up nor concave down. So this leads us to what we also want to talk about called points of inflection. Now, a point of inflection, or very often I'll just abbreviate that a POI, is a point at which the concavity changes direction. And if you look at this graph, I've got this blue dot. It looks like it's probably about at the origin, because somewhere near the origin, it appears that this graph stops being concave down and begins being concave up. Now, the good thing about that is, notice I said it stops being concave down and starts being concave up. That means that the second derivative has to change from being negative to being positive. And that can only happen if the second derivative is 0 or undefined. So a point of inflection will always occur at a point where the second derivative is 0 or undefined. Now, that does not mean that every time the second derivative is 0 or undefined that there is a point of inflection, but those are the only possible places where points of inflection could occur. So let's look at this function that is graphed here a little more closely and see how we would determine its point of inflection. So you can see here that I've given you the equation f of x equals x cubed minus 4x. We want to take the second derivative of that, so that means we have to first take the first derivative and get 3x squared minus 4, and then take the derivative of that and we get 6x. We want to find any values where that second derivative is 0 or undefined. Well, that's pretty easy. 6x is defined everywhere, so we don't have to worry about that, but we do want to know where does 6x, the second derivative, where does that equal 0? Of course, that would be when x equals 0. So what we're going to do is, just like we did with the first derivative and minima and maxima, we're going to do the same thing to locate inflection points. We're going to divide up our number line at any number that we find where the second derivative is equal to 0. In this case, that's at 0. Then we're going to pick values on either side. I always like to pick the easiest one I can think of, and in this case, since we're splitting at 0, -1 seems like a good value on the left, and +1 seems like a good value on the right. Once we pick those values, we're going to plug them into the second derivative. And of course, 6 times -1 is -6. That means that everywhere from -infinity up to 0, this function is concave down. And then we plug in +1, and 6 times +1 gives me +6, which means that everywhere from 0 to infinity, this function has to be concave up. And since the point at which the sign changes is 0, then we know that the x value for the point of inflection is 0. And to find the y value, now we need to plug that all the way back into f of x. And 0 cubed minus 4 times 0 is 0. So we found that the point of inflection is, in fact, at the origin for this function. Okay. There's one other important thing we can do with the second derivative, and that's called the second derivative test. Just like the first derivative test, the second derivative test is to help us find relative extrema. Okay. And so what we'll see is if f prime, that is, if the first derivative is equal to 0 and the second derivative is greater than 0, then that point where that occurs is going to have to be a relative minimum. So let's look at this red graph. We know that the first derivative is 0 when we have a horizontal tangent line. So see how we have a horizontal tangent line there? And we already know that that red graph is concave up. And you can see that that makes it so that that point has to be a relative minimum. In the same way, if the first derivative is 0, but the second derivative is negative, then we're looking at a point like that, like the top of that green graph, where we're going to have a relative maximum. Now, the second derivative test is actually less powerful than the first derivative test, because the first derivative test can find extrema if the first derivative is undefined, and it can also find extrema in other cases. For example, if f prime of c is 0 and f double prime of z is also 0, then we're going to have a case where the second derivative test fails. It just doesn't give us any information. And you can see with this purple graph down here at the bottom that that's the case. So this is a graph of 1/12 x to the fourth. When we take the first derivative, we get 1/3 x cubed. And that derivative will be 0 when x is 0. And it's defined everywhere. So we're looking at the origin as a possible point, possible extremum. And if you just look at the graph, it seems pretty likely that it is an extremum. But then we go ahead and take the second derivative. The derivative of 1/3 x cubed just gives us x squared. And the problem here is that when we are at 0, the second derivative is also 0. And so even though we can pretty clearly see from this graph that 0, 0 would be a relative minimum for this graph, the second derivative just fails to give us that information, because technically at that point that graph is neither concave up nor concave down, even though it looks like it's concave up everywhere. It really isn't. It loses its curvature there at the origin, and because of that our second derivative test fails, and we would just go back to the first derivative test, and we could pretty easily use the first derivative test to show that the origin is in fact the minimum for that particular function. And that's how the second derivative test works or fails to work.